Hello everyone, welcome back. This is Frank. Let's continue our journey of Pytorch XLA. In this lecture, we're going to take a closer look of capturing the computation graph. Especially, we will take a look at the lazy tensors and tracing. Before we jump into today's content, let's take a quick recap of our last lecture. So in last lecture, we talked about the standard Pytorch eager execution that sent many small operations to accelerators. The problem of this action is that it launches many small kernels and create what we call kernel launch overhead, and it underutilizes the accelerators that you have. So the XLA optimizes the computation graph for accelerators. Pytorch XLA aimed to bridge the Pytorch usability with XLA performance by running Pytorch code through XLA. In today's lecture, let's take a closer look at how XLA actually captures the computation graphs from your dynamic eager style Pytorch code. Remember that there is a fundamental conflict between Pytorch and XLA. Pytorch is a dynamic framework. It executes your command line by line. That is, the Pytorch framework has no idea on what you're going to do and what your computation graph look like while it's executing. It's just execute line by line and follow the instruction. However, XLA needs your full static computation graph before it can optimize and compile and execute your code. So that is the fundamental conflict between Pytorch and XLA. So how can we bridge them together? The solution provided by Pytorch XLA contains two parts: the data and graph capturing mechanism. Let's first take a look at the data part. Remember that the standard Pytorch tensor holds actual numerical value in memory, whether you're using GPU or CPU. The operation on the traditional Pytorch tensors will be executed immediately. That's what we call the eager execution. An XLA tensor doesn't immediately hold the numerical result of computations performed on it. Instead, it acts as a placeholder or a node. It stores the information about how its value should be computed instead of the value itself. So how can we get a lazy tensor? When you move a tensor to XLA device, it becomes an XLA tensor or a lazy tensor. If you think of a standard tensor like having a $5 bill in your hand, an XLA tensor is more like a box containing a note saying that there is a $2 bill in box A and there is a $3 bill in box B. If you get both of them, you get $5, and that's me. In other words, you have a description of the value, not the value itself. Here I copy the definition of the lazy tensor from Pytorch XLA. As you can see here, a lazy tensor can be created from a regular tensor. The most important member of a lazy tensor is data, or a pointer to a data. So the data has three most important members: a backend data pointer, an IR value, and an optional tensor data. A backend data pointer is a pointer to the data that's stored in the backend device. In our context, that will be XLA device. The IR value represents intermediate representation. It's basically a node in the computation graph. The optional tensor data is the actual tensor data. So those three members are mutually exclusive. You either have a pointer to the data that is stored in your accelerator, which is the first option, or you have intermediate representation of the computation that you're going to perform to get the value of this node, or you hold the actual value. So it is not that a lazy tensor cannot hold the actual value. It is that it can hold intermediate representation, which is a computation that helps you to get the current value. So now let's take a look at the second part, which is the tracing mechanism. The lazy tensor changes the traditional Pytorch tensor. The tracing mechanism changes the traditional Pytorch operator's behavior. Pytorch XLA uses Pytorch dispatch mechanism to intercept calls to standard Pytorch functions and operations. Instead of executing the computation immediately on your CPU or GPU, it records the operation when operation involves one or more XLA tensors. So here is an overview of the tracing mechanism. The Pytorch XLA will first intercept all the Pytorch operations. Instead of calling the default operation kernels, it calls XLA special kernels for that operation. XLA kernels don't perform mathematical computation. Instead, it records the operation and its input into an internal intermediate representation, the IR. Remember, the IR is the node in the computation graph. Then it returns a new XLA tensor representing the future result of the recorded operation. This new tensor becomes a new node in graph, connect to its input. So here I have a little diagram show the whole process. For example, we have z equals x plus y. Suppose x and y are lazy node and they hold actual values. The z equals x plus y. Instead of computing the actual values of x plus y, it records this addition operation into an intermediate representation, which can be held by the lazy tensor. In this example, z doesn't hold the actual result of x plus y. It holds an operation, which is an addition of x and y. This is the magic of how Pytorch XLA forms computation graph from Pytorch code. After capturing the computation graph, let's move to the last part, which is the triggering of compilation and execution. The graph needed to be compiled by XLA and executed on the accelerator. The triggering happens when the actual numerical result is required or when explicitly told to run. You can explicitly trigger the compilation and execution of a computation graph captured by Pytorch XLA by having torchxla.sync line in your code. This is previously marked step, but the Pytorch XLA team recently started to encourage you to use torchxla.sync. By having this line in your code, you explicitly tell the framework to stop recording and start compile and execute the existing graph. There are many situations that you actually need a numerical value result before moving forward. For example, when you print a value, instead of printing a recipe of getting the value, users expect to print the actual result of the computation. Other situations like getting a scalar values, convert values to CPU, move the value from XLA device to CPU. When you save a tensor value, or you meet some conditional logic in Python-based tensor value. For example, when you say if a tensor value is greater than 0, then you execute one branch, or you execute a different branch. In that case, you have to first get the numerical value of your tensor before move forward. This can be problematic and break the tracing and defeat the whole purpose of building a computation graph. So be really careful of using if statement or for loop in your XLA code. Let's jump into a demo to see all the concepts that we have just talked about work together. Let's move to our Python node to run our demonstration. If this is your first time using Pytorch XLA, uncomment this line to install the dependencies that you will be needed in this demonstration. Let's move to our code. So first we import Pytorch and XLA. Then we define two simple tensors, x and y, which are 2x2 tensors. Please notice that by the time when they're defined on CPU and their values are saved in memory. In next two lines, we basically move the values from CPU to XLA device. So we basically move the two tensors from CPU to XLA device. Remember that by moving the tensor, you're creating a lazy tensor. Then we perform the operation, which is addition. Z equals x plus y. At this point, z actually doesn't hold the actual value. Instead, it represents a node in the computation graph. Let's try to run the code. Okay, after about 1 minute of loading, we finally get the end of the first block. It doesn't print anything. You just have the faith that z doesn't hold the actual value. However, there is a way that we can print out what z actually contains. We can inspect the graph using an internal API, which is getXLA tensor text. This API is not for production use. It's only for debugging and development. So we just print the value of z. As you can see here, what's printed is an IR value. Z actually contains the IR value instead of the actual computation result. And this text actually represents XLO, which is high-level optimizer. And as you can see here, you can kind of guess what it does. You have some symbol 1 represents 2 by 2, and you have a symbol 2 represents another 2 by 2. And on the step 3, you have latent addition of 1 and 2. So even though you don't really understand what this text represents, but you can pretty much guess what it does. It actually contains a computation that adds symbols. Now let's move down to let it actually compute the result. Remember that there are actually two ways to trigger the compilation and the execution of the computation graph. By explicitly call this sync or by printing the value. Let's try to explicitly trigger the computation. So here you can see when we print the value z, it's actually print the values and it tells me, yes, it's on XLA device. Here you may say, wait, we directly print the z. This is probably different than what we did from the last step. Now let's try to execute the same print again. You can see the IR value actually change. Instead of an addition of two values, it actually only contains a value. And it's a device data. And it contains its shape. So it's more concrete value than an operation. I hope this simple demonstration can help you to understand the basic idea that we just talked about in this lecture, the lazy tensor, the tracing mechanism, and the triggering mechanism. Here is a brief summary. XLA tensor doesn't store the computed values immediately. They record the operations and build the computation graph. The actual computation is triggered only when you need the result, like when you print the result, when you have an if statement that depends on the result, or when you explicitly trigger the compilation. This mechanism enables Pytorch XLA to first capture the whole computation graph before actually executing it. This enables optimization like fuse operations for more efficient execution on accelerators. That's all for the demo. Let's move back to the slides for a summary of our lecture. In this lecture, we learned that Pytorch XLA bridges dynamic Pytorch and graph-based XLA using lazy tensor, a tracing mechanism, and a triggering mechanism. Lazy tensor is a placeholder or a pointer to IR representing the future value on XLA device. And for tracing, it intercepts the regular Pytorch operations on lazy tensors to dynamically build a computation graph. The actual computation on the accelerators is deferred until they are explicitly triggered by using torch XLA.sync or implicitly triggered by accessing the value. Either you print the value or you need the value for the next step. That's all for this lecture. In the next lecture, we will take a deeper look and see more details about this mechanism. We will see what the XLA compiler actually do with the IR that it collects. We will have more details about the graph building, the compiling, and executing. Stay tuned and see you next time.